Sorting is a process that is often implemented in computer programming. In fact, it isn't hard to come across instances where something is sorted in everyday use of computers. For example, let's go to youtube.com and pull up the CompSci study channel. When we click on videos, we have some options here. These allow us to sort the videos in a particular order. The videos are sorted with the latest videos showing first by default. We can sort by popular, which sorts the videos by view count, or we can sort by oldest, which sorts the videos with the oldest videos showing first. Now, whether you are browsing YouTube or another website, using one of many popular productivity apps, or playing a game, data is often sorted when displayed to a user, or the application allows for a user to sort data or content in a number of different orders. Now, sorting data is not a topic that should be quickly skimmed over, and for that reason it deserves its own playlist on the CompSci study channel. The core of the complexity of sorting data, and the reason why some have made it the primary focus of their studies, is in the fact that there are multiple ways in which a specific dataset can be sorted to produce one particular order. For example, here is a group of single-digit integers. If asked to copy the integers to a new list, with them sorted from left to right, smallest to largest, one person might start by first finding the smallest integer, being 0, and copying it to a new list. Then the next smallest integer, being 1, and copying it to the new list after 0, and so on until all digits have been copied and sorted from smallest to largest. We'll call this the start small algorithm. Now, another person might start by first finding the largest integer, being 8, and copying it to a new list, then finding the next largest integer, being 4, and copying it to the new list before 8, and so on until, just like the first iteration, the digits have been copied and sorted from smallest to largest. We'll call this the start big algorithm. Here we have two separate algorithms that achieve the same ordered set of integers. Now, in this case, both algorithms took the same amount of steps to obtain the ordered sets. However, this is not always the case. If we could cut the amount of steps in half, or maybe even by more, we can sort data faster and decrease the stress on a computer when the task is being performed, freeing up space for more tasks to be ran. This is why some computer scientists and mathematicians dedicate their lives to studying and publishing sorting algorithms to improve the sorting process. Now, without getting too much into the topic, the time it takes for a sorting algorithm to run is called time complexity. Sorting algorithm time complexity can be represented using big O notation, allowing the various algorithms to be compared. We will cover time complexity and big O notation in another video. For this series, just know big O notation is what we will use to measure and label the time complexity of the sorting algorithms covered in this playlist. Now, some sorting algorithms are more difficult than others to mentally process. While simple algorithms will be easy to mentally process, oftentimes they are less efficient than more complex ones. While this isn't always the case, it often is, and efficiency should always be valued more than simplicity. The sorting process tends to be performed in order to increase the efficiency of algorithms used for other processes, like searching. For example, suppose there are 10 people standing side by side in no particular order. If asked to find the third tallest person, the person can likely be found quicker if the 10 people were already arranged from tallest to shortest.